Welcome back to the CS128-Honors video. In this lesson, we'll be talking about ownership in regards to threads and continue our discussion about threads from last lesson. So, why doesn't this code that Eustace showed off at the end of the last lecture not work, right? Well, if we look at this code here, what's going on? Well, for starters, we have this variable v, and the variable v is being borrowed into this closure, right? So this variable is now inside the closure, but it's being owned by the outside thread. Now, the issue is that this is actually not going to compile because v is still technically owned up here, right? And when you have v owned up there, then Rust doesn't know when it will be able to get v back from this child thread. It doesn't know how long that thread is going to last. And so what you'll get is you'll get a nasty compiler error that will look something like that. And so it'll say, as you can see, may outlive borrowed value v right there. And so what you need to do here is you need to be aware that it's giving you advice, right? So if you look, it tells you, hey, use the move in order to move those variables over to the thread as opposed to just borrowing them. And this way you'll be able to avoid the issue where the lifetime of v is indeterminate. So if we look at this code again, let's take a look at an example where v being an indeterminate lifetime would be a problem, right? And so if we look at this code, we first start off with v and we move it, or we borrow it inside here. So now v is being borrowed here, but it still is owned right there, right? And so now we have this code that's being owned elsewhere, and now we need to go back to our main function while this second thread is running. We're now going to have a new line in here that will drop v. And so in case you don't know what drop does, it will release the memory for v and mark it as no longer in use, right? So now this v down here is going to not be owned anymore by this function, and it's no longer going to be valid here, right? And so the issue with that is that Rust can't, at compile time, determine in what order this is going to happen, right? Because just like we saw with the last lecture, when Eustace was presenting, it could be that it runs this line first, then this line in that second thread, and then it goes back out and it finishes. Or it could be that it starts with that line, then this line, and then skips that line as it's booting it up, drops v, then goes back and tries to use v, and then tries to rejoin that thread. And so as you can see, these different execution orders can drastically change whether or not v is there, and Rust can't guarantee that v is there. And this is a very important part about the Rust ownership model, is that it is trying to prevent mistakes like these from happening. Because if you tried to do this in C or C++, at least something similar anyway, this would 100% work and would lead to runtime errors that you might not be able to track down. So what we can do, as I mentioned earlier, is we can use the move keyword inside of our thread spawn and in front of our closure. And what this will do is it'll tell Rust, hey, instead of trying to borrow v, move v over, right? It'll be just like if we were to clone it, except instead we're moving it. And this way, now handle is going to have the ownership of v instead of main. So main will no longer be able to access v, and this way v is able to be printed out in here. Now this works great, but now the question of, okay, what if we want to access it back in the main thread comes up, right? And so if we were to add that drop v back in, now v no longer exists up here, right? It now exists over in this thread. So we can't access it up in the main thread. And so when we do this, you now need to be aware that drop v is no longer going to work. And so what's going to happen is we're going to get a compiler error that we have moved it over and we haven't copied it, right? And so you'll see value used here after a move. And so this isn't allowed by Rust, and this is why we need to be careful about when we decide to move versus borrow, because we might want to do one or the other. So now what if we want shared data, right? What if we want to be able to have data that two threads, or maybe the main thread and a side thread, both can use? Well, to do this, we'll use what's called a mutual exclusion, or a mutex, right? And so the mutex is basically going to prevent threads from accessing the same data at the same time. And so let's take a look at that. So mutexes, as I said, allow you to share data between threads, but they prevent race conditions like the ones we saw above by only allowing one thread to modify that data at a time. And so the way this is done we'll show off in a second here by using a very ominously presented here rubber duck. And so what this rubber duck is going to represent is our mutex. And basically the idea is that only one rubber duck exists and you can only modify the data while you have the rubber duck. And so let's take a look at that. So we have two threads here and we have a couple of Ferrises that will be acting as our sort of thread personas here. And we have the shared data here, right? So this is shared between the two. And so we have the shared data with a value of 10 inside, and then we have a mutex that is determining which thread is currently holding it and can modify the data. So if we look at this example, what we're going to start off by doing is having thread 1 take the mutex. So this means that thread 2 can no longer access, that is really hard to see, thread 2 can no longer access our value of 10 there, right? It has to wait until thread 1 is done. And so now that thread 1 has has its own access to this value, it can modify it, and in this case we'll change it to 15. And so now let's say while it's modifying 15, the other thread finally runs into this and is trying to change this value. So what the system is actually going to do is it's going to say, nope, you can't modify that until thread 1 is done. And so this is done through a little bit of wizardry at the system level, but what you need to know right now is basically thread 2 will stop executing until thread 1 is done. And so now when thread 1 finishes, it can return the rubber duck, and now thread 1 can continue going on its way, and it cannot modify this value over here. But now that the rubber duck has been returned, thread 2 can take the rubber duck and it will no longer be blocked, right? You can now go into thread 2 and continue running and modifying that value. So now thread 2 can modify it to value of -32, and thread 1 will not mind because it's not trying to access it. If it did right now, then it would have the same thing that thread 2 did, where it'll block until thread 2 is done with it. And so then finally thread 2 will return this value, or the rubber duck, to this variable, and now either thread the next time it runs into it could pick up the rubber duck and make its modifications. Now one thing to keep in mind here is that every time that you're working with these threads, you need to make sure to release the duck, right? Because if this duck is still being held by 2 and thread 1 needs it for something and thread 2 never finishes or never releases the duck, then thread 1 now becomes stuck. And this can become a cascading problem that you usually see in other programming languages like C or C++. That isn't so common in Rust, but it's something that you have to be aware of. And this is what's called deadlock, as Eustace referred to in the last lecture. So let's take a look at an example of a mutex in code. And so we're not going to talk about mutexes in the context of multiple threads just yet, because you'll need some of the stuff from next lecture. But in the meantime, let's take a look at it in a single threaded context. So what we have here is just an import of mutex. So that's just importing the things that we need. And then we're creating a mutex, and we're passing in a value of 5. And so what's interesting about mutex is that it's actually a generic type, which if you remember from something like Java or C++, will actually allow you to pass different types in. So right now we're having a mutex lock of the int 5, but we could have a mutex of, say, a string or a character or something else, right? This doesn't just have to be integers, but that's what we're using it in this case for. And so now inside this closure, you can pretend that this is a separate thread. We're now saying, okay, get our number from the mutex. And so what we're doing is we're calling mutex.lock, which will say, okay, if there are any other threads holding the duck, wait until that thread is finished. And then once it's done, then give me the value inside of there and unwrap it. And so this unwrap, just like with thread.join, is used to make sure that we're not having any invalid issues with getting the mutex lock. And then finally, we take that value, we dereference it, and we set it to a new value of 6. And then once we're done, we can print out that value, and we'll get m is equal to 6. So yeah, that is threads and ownership. I hope you enjoyed this lesson, and I will see you in the next one.